everyone. My name is Wajahat, and this is Wongkyung, and we are from Honk Technologies. And today, this is a demo of our product called Sioux, which we are building here at Honk Technologies, basically. So, how I'm going to do the demo is basically I'm going to tell you some stuff that I know, and you can see like a live transcription and translation basically in your own language, and you will be able to better understand what I'm trying to say. So, what I will talk about today is basically something called LLM, and nowadays they are pretty hot in the market basically. So even if you don't know like what it means, or like if you have like a vague sense of what LLM is, so today I will try to let you know a little more about that. So, for example, if you have never like heard about LLM and you don't know like what is he saying, like what is LLM actually, and how or when I have used it. So, if I write this thing like, then I'm pretty sure like you might have used this ChatGPT or Claude or Gemini. So you might have used this, or you might have even have like subscription of this, and essentially all of these are like LLMs. And LLM is a short form of like something called large language model. So you see LLM, so that's why large language model. So, and basically what are they? It is essentially like a type of a neural network. And neural network is an algorithm basically of an AI. So it is LLM is like a type of neural network, and I will try to teach you guys like how does it work, like how we essentially like create an LLM. So to make an LLM, essentially there are three things. One is neural network algorithm, and the second is like data, and the third is like compute. So basically, like you have to have some kind of algorithm, and you need to have some kind of data, and you need to have like some kind of compute. And by the mixture of it, like you do some magic, and then you at the end you get an LLM. And the magic is essentially like it's called training. Like you train a neural network on top of data using a large amount of compute, and that's how you get an LLM basically. So these three essentially are like the three pillars of an LLM basically, right? So how do you do that essentially? So there is something called an objective function in training, and which is common in this like training these neural networks. Remember, like LLM is like one type of a neural network, and there are like bunch of other type of neural networks, and it is just one type of neural network. And what you do is like you train these neural networks, right, on data using some compute, right? And all of these neural networks have essentially something called objective function, and this thing is very important. So essentially like an objective function is like a function on that is like an end goal for your you're training your algorithm basically, right? So the objective of an LLM is like pretty simple. It is like predicting the next token. And here token you can think of as like as a word basically. So it's so it will be like much more easier for you guys to understand. So basically like objective of a the objective that we are trying to train an LLM is like we want it to predict the next token. And how do we do that? So we give it like huge amount of data and huge amount of compute, and basically what we're trying to do is it is like we want it to predict the next token. And how do we do that? For example, I have an example like let's take a sentence. He is reading a book and the other one is sleeping, for example. So this is like a pretty normal sentence. Like he is reading a book and the other one is sleeping. So it is a sentence, and it is like one of the like millions of sentences that we have in our data, and we are like now trying to guess like, okay, like we need to train an LLM, so what we will do. So as you guys know, like our objective function is like, okay, we want the LLM to predict the next token, and this is the data, right? So we have to do something with this data that can like help the LLM in predicting the next token. So what we will do is basically we will mask some of the tokens, and by masking I mean like we will remove. Sleeping basically, right? So for example, this will be like fill in the blanks, right? So okay, now this is a fill in the blank for the LLM, and this is he needs to solve it basically. So we will mask these words basically. We will mask some tokens of the sentence, and then we will train the LLM on this masked words basically. We want it. What essentially we are trying to do is like we are trying to make it learn basically like uh, that he needs to learn like what exact word will should be placed in this sentence here. So he is dash a book. So normally, what do you do with a book? I guess you read a book, and since it's is, so it should be he is reading a book. And the other one is dash. And now this is a good one because like a bunch of words can essentially come here, right? But like so it can be like playing, it can be sleeping, it can be like a bunch of things. For example, he's sleeping, he's playing, and he's eating, that kind of stuff, right? So essentially, like we want our LLM to be very good at this kind of task. Basically, we want it to be very good at predicting the next token. So how do we make it that good at it, basically? So there are three things, right? I told you like neural network, data, and compute. So we will talk about it one by one, basically. Let's start from the downward because it's much more easier. So compute. Compute basically means like we want to have some GPUs that we want our LLM to train on, right? And why are GPUs essentially like good at this stuff, like this training of these LLMs, basically? So why the reason that they are good at this stuff is like on the very core, what our LLM is trying to do is it is doing something called matrix multiplication. So basically, it has different matrices, and what it wants is what it is doing is it is like multiplying all these matrices, and like for example, these are a bunch of matrices, and it is just solving these matrices to give to give the next answer. So basically, GPUs are very good at this stuff, matrix multiplication, and whole of like this algorithm essentially is just this matrix multiplications, right? So jumping on to the next one, the data. So nowadays we have a very good thing called internet, and there's a lot of data available on the internet, right? So what we will do is like we will take all the data from the internet, and we will like train our LLM with like huge amount of GPUs, and we will train on this in this huge amount of data that we have scraped from the internet, and we have like we should have like a lot of compute. Like it won't work like on just a few GPUs. We will have like a lot of GPUs, and we will do this matrix multiplication basically, and at the end we will get an LLM basically. And the most important thing is like something called a neural network, the algorithm basically that we are trying to do. So uh, this essentially this is like a text, right? This is a text, and in the term of like theoretical terms, it is an NLP task basically, right? Natural language processing task it is, and before like LLMs, there were other architectures, other neural network architectures that were being used to solve these kind of different texts, right? So essentially, like, but what came like that the LLM became so good at it? So it was because of something called attention mechanism, and it was introduced in a paper in 2017. It's called "Attention is All You Need" paper. So basically, what the authors of this paper were trying to do was they were trying to do a similar task called machine translation. So what they wanted to do was like they wanted to translate a sentence from one language to another, right? So similar to what we are doing actually, right? So So they wanted to solve this particular task, which is a very simple task from NLP domain. And to solve this task, they introduce a new architecture called a transformer. A transformer model. So if your background is like me from electrical engineering, you might think this is like electrical transformer. Actually, it's not. It's a AI or deep learning transformer, and that's like a bit different transformer. So the most important part of this transformer is actually something called attention mechanism. So what is attention mechanism? So for example, if you're trying to get like an intuition about this, so let's look at the sentence. He is reading a book and the other one is sleeping. So as humans, when we read this sentence, we are like, oh, he is reading a book and the other one is sleeping. So we kind of know, like, okay, it's one person. There are two persons in this sentence. One is reading a book and the other one is like sleeping, and they are doing two different other tasks. And we know, like, the first one is this: he is reading a book, and the other one is like sleeping. Not the first one is sleeping and the second one is reading a book. So we know the context of it essentially, and it's very difficult for a neural network to actually learn about this kind of thing, because before there was another from a neural network called RNN, a recurrent neural network essentially, and it was also like before like this transformer models that use attention mechanism, it was very popular. But the problem with this was like it was a sequential architecture. So for example, there's a sentence like he. So what it was doing was it was sequentially it was trying to like predict the next word. But the problem with and in here there was something called hidden states, which was essentially its memory, and it stored the information and it like projected into the future and future and future. But the problem was like somewhere in the future it forgot like okay what it was saying, because like it will start from he and by this time it forgets like oh what was he about and what was reading about, that kind of stuff. So to solve that kind of problem, like transformers were introduced. And why they were good at it was like if you look at this, it is a sequential architecture and it is like one by one. And this attention mechanism, what it does is like, for example, we have this word reading here. It will at the same time look at all these words basically, right? Like it will basically like see all these words of this sentence basically, like and compute like attention between this reading and this he is the book and the other, all of these sentences, attention will be computed. And the output will be some kind of out of something like this attention map. And in this attention map you will have like, for example, this sentence, he is reading a book, is written here, and he's reading a book is written here, and then you compute like attention between them, and your output will be something like this. Like in the middle the attention will be highest because like they are computing the attention among itself. And for example, if you see the reading, it's very much so what attention tells us, it tells us like how much a word is more closely related to another word. Basically this reading, how much it is related to is he a book. So for example, since it's reading, so the attention between like a book will be very higher because it is directly related to the book, right? You read a book. And the reading and with sleeping will be very much lower because like reading and sleeping don't really have much connections. And this reading with this he will be very much high because this person, this he is actually reading a book, right? Not this other one actually, right? So for example, here if we see like, for example, he starts from here and he starts from here. So for example, the third one will be reading, right? So this reading and this he will have like high attention like between them, essentially you can see it like as a similarity, high similarity among with this he, right? So it means it shows like this person is actually reading a book, right? And the other one is doing some other action. So basically this attention mechanism, if a while ago I talked about this matrix multiplication. So the formula is actually like this, and there's also like some other stuff like this. It is divided by like this dictionary, and there's also like a softmax. But let's not talk about this, and let's focus on these three terms: key, query, and value. So if you see, all of these are like multiplied with each other, right? And if you remember, I said about like there's a lot of matrix multiplication. That's why like GPUs are very important, right? So if you see, like we are multiplying these matrices, the key, query, value matrices with, and this each and every like token will have its own like key, query, value matrices, and we will multiply with all of the tokens, and we will get some, response. And the basis of that response, we will know, okay, this reading is very much highly related to he, and this is related to a book. So then, like, our LLM will know, okay, this he person is reading the book, not the other person, basically, right? So that's why they are very good at it. Essentially, like what they are trying to do is like they are predicting. We are training them to predict the next token, but with the help of like huge data, huge compute, and this transformer architecture, uh, which is based on like attention mechanisms, self-attention, and multi-attention mechanisms. It gets, if we like train it on like huge amount of data, essentially the whole internet on a lot of GPUs, it gets so good at predicting the next token that it like forms coherent sentences and stories, coherent stories. If you have used any of these like LLMs, basically, they are predicting the next token, and while doing the prediction of the next token, they form coherent sentences, and in those coherent sentences form coherent paragraphs, and those coherent paragraphs form coherent like whole essays. So why they are coherent is essentially because of this attention mechanism. Because before, with RNN and stuff, like it was not possible like that. In the middle, you forget the context, and you don't remember like which sentence was like this, which sentence meant what, which sentence connected to what. And but with transformer architecture, and in and LLMs, LLMs are basically scaled transformer architecture. Like the architecture has not changed, because if this paper, when this paper came, the architecture is same. It has changed, but it is like incremental increase, not like something different came, and there's now in the LLMs there are some different architecture it is being used. It is the same transformer architecture, but it is a scaled version of it. There's another thing in the researchers found is like scaling laws. Basically, what they mean is like you scale any of these three things. Basically, you scale any of these three things, the performance of the LLM will increase a lot. Basically, like if you train your LLM, your model with more data and more compute, and the performance of it will become better, basically. And what is the reason for this? Actually, the reason, if you think intuitively, it is because like all of this neural network have some kind of thing called parameters that we tune and train, right? And you can think of this parameter like they are learning some kind of knowledge, right? So if the size is bigger, you will have more capacity and capability to learn more knowledge, essentially. Like, so the bigger the model, the more knowledge it can hold, and the more context it can find, and it is better because it has more knowledge, and it is more like context, essentially. It is like you are training, it's similar to, like, for example, if there's a human, and he just knows one book, and there's another human who knows like 10 books. So the 10 will for sure be better than one, because he has like more knowledge, and he can make like different connections between all those 10 books. So he will be better. So these are essentially scaling laws. So what the researchers find was like you keep the architecture same. There has been some incremental increase in the architecture itself, but mostly what the people are trying to do right now is like they are scaling that on the data and on the compute. And nowadays we have like even trillion parameters model, which was like unthinkable a few years ago. So um, basically, yeah. So this is your LLM, and I hope you have like some intuitive understanding to like how it works. Like LLM is like a neural network that is trained on some data with some compute, and what we are training it on is basically we want it to predict the next token. We have this data set, we mask some of the words, and we pass it through the LLM, and we want it to predict that masked word, basically. And by doing it, it gets so good And at the end you get like something called ChatGPT, Claude, Gemini, which essentially like started as some kind of chatbots, but now they are like much more in chatbot that they can do like a lot of stuff. Like they can help like they can like help you in coding, and they can write the whole essays. They can write like like pretty good, because like chatbot is very old concept. Like it was even like in 80s and 90s, but those were like could only couldn't even form like a few coherent sentences. But like if you look at like ChatGPT and Claude today, they're like pretty great at this. So they cannot be essentially called chatbots. So they are LLM. So yeah, so it has like three components. In your network, you have like your transformer architecture, you have your data, which is the whole internet, and you have your compute, which is the lot of GPUs basically. And using all of this, you train a model, you train an LLM, and it becomes so good at predicting the next word that it is at the end you don't think about like, oh, it's just predicting the next word. It is like it is giving you like much more information. So I will end this talk by like giving by saying a quotation from a researcher called Ilya Sutskever, which was like one of the fathers of the field. And if you can think about like this, like predicting the next token is like pretty simple thing to do essentially. So how can like at the end, if we just on this top of like simple thing, how can like an LLM can be so good at so many stuff, right? So he said, like, for example, I will give you a book, and on the book, like, it's a detective novel basically, and you have to go through every word. Like you read the whole novel essentially, and the last line of the novel is and the murderer is. So fill in the blank, right? So if you have read the novel pretty well, you will know, because all the evidence is inside the book, right? So if you have read the novel pretty well, and if you know, okay, like something happened, this happened, he went away, he came back, something like, so okay, I know like who the perpetrator is, like who the murderer, or like whatever the novel is about, right? So that's the thing, like essentially we are trying to train them. So on this like masking one word, and we train it so much on such a huge scale that at the end they become so good, like they're not just next token predictors, they are like LLMs. So yeah, I think I'll finish my talk here, and it was fun having talk with you. Hope you had like some a little better understanding of what LLM is like, and I'll be back again next time to teach you some other stuff. Yeah.
All right, Wajahat, thank you so much for the lecture. And yeah, so there's this QR code right here on the screen, as you can see. You can simply take a photo of it, or you can scan it to see the transcript being made and all the translation in the language that of your choice. So thank you so much, and we'll be in touch later. Bye-bye.
Bye.